Hello, welcome back. Today we're going to be looking at liquids and solids. We left off last class talking about gases, specifically the kinetic molecular theory, which talked about those um, five assumptions we can have of gases. So we talked about the density of gases, the way they move, their fluidity, things like that. So today we're going to get into the properties of liquids versus solids and then be able to compare the three of those and then get into the crystalline shape of solids a little bit here. So with liquids, we're going to go over these six properties of them in detail. So I won't talk about those right now, but I want to pull your attention to this graph. So if you look at this graph on the side, we have temperature along the bottom, pressure on the side, and you can see that there's a wide range of pressure where solids can exist. There's a really wide range of pressure and temperature where gases can exist. But if you're looking at liquid, it makes up the smallest portion of this graph. So that has to do with the special properties of liquids. Okay, so liquids can only exist in this small portion of temperature ranges and also a relatively small portion of pressure ranges compared to the other two states. So liquids kind of have a unique set of properties, and we are going to talk about that. We will eventually also look at like triple point and the critical point. So if you're talking about water, the triple point is where you're at a certain pressure and temperature where that can exist in all three states at the same time. So that's also kind of cool. We'll get to that later. But if you also look at this, there's a nice description of kind of like melting to freezing, vaporization to condensation, sublimation, and deposition. So if you are not familiar with those words, you don't remember them from physical science, you might want to revisit them, especially sublimation and deposition. It's ones that sometimes we forget. All right, so the first property is going to be fluidity. Okay, so we talked about fluidity with gases, saying that gases are very fluid. Okay, fluidity just means that the particles are not very attracted to one another, not enough so to stop their motion whenever they come into contact. So gases are super fluid. They're just going to slide right on past one another. Liquids are also fluid, but they're much more attracted to one another than gases are. So if you're looking at this diagram on the right-hand side, this is supposed to be representative, kind of of the space between them. In all honesty, gases are much more spread out than what this picture is representing. So if you look at liquids to solids, liquids are much more tightly arranged than a gas, but just not quite as much as a solid. So because of this, your liquids are going to have relatively high densities. Okay, they're going to be just maybe slightly less dense than their solid forms, and they're pretty much incompressible. Okay, so you can compress a liquid just a little bit, but really not very much. So a gas, you could compress this like 99%. Liquids, you can only compress about 4%, in solids, 0%. So if you're looking at these in comparison, just be aware that liquids and solids are much closer, much more similar to one another in terms of their energy levels than gases are to liquids. Another thing about liquids is that they are able to diffuse pretty easily. So we talked about that a little bit with the gases. We know that gases can diffuse or effuse. Basically, they're going to spread out, intermingle with the other particles around them. So liquids will also do that, and it diffuses at a higher rate with more warm temperatures. So if you have a hot liquid versus a cold liquid and you drop some dye in it, for example, that's what these pictures are of, it's going to diffuse much more quickly in the hot water, and that has to do with the way the motion of the particles. So if you add energy, you're adding kinetic energy to the water, the particles are moving around much more quickly, and in turn, it's just going to mix everything together much more quickly. Liquids also have surface tension, which is unique. Okay, it's the only phase of matter that has surface tension. Okay, and this comes from the force of your molecules to be more attracted to one another at the surface. Okay, so the adjacent parts, like if you're looking at this picture here, these two particles are going to be more attracted to one another than they are to anything else around them. So you have an attraction throughout your substance, right? But because there's nothing else to be attracted to along the top side, you kind of get these polarized attractions here where you have a stronger attraction between the particles on the surface. Because of this, you're going to get capillary action. Okay, so capillary action is hopefully something you remember from biology. If it's not, you're talking about the way that particles will be attracted to one another and the surface of a solid. So if you think about a glass of water, right? So if you have a glass of water with you, or if you're not familiar with this, go get a glass of water, clear glass, put some water in there, and then get eye level with the level of the water and look at the sides. So on the sides, you're going to have where it looks like it's a little bit higher on the sides, then it's lower in the middle. This is also called the meniscus if you were measuring things in class. And that happens because of capillary action. So in that glass, our theoretical glass, you're going to have a higher attraction between the particles and the solid, which is the side of the glass, than they are to each other. So it's going to be kind of like pulled up around the sides, and they'll be more attracted there. You can use capillary action to your benefit. Okay, so there's a couple of the ways that you can do this. So it's basically pulling liquid upward along the surface against gravity. So if you've ever had to siphon anything, so like siphoning gas, you are starting the process, but then capillary action takes over. Okay, so once you get the liquid flowing, capillary action is going to continue to pull that liquid out of the container upward, out of the container, and then obviously it'll fall back out as the tube bends downward. Another example of capillary action could be if you ever had to do like a blood sugar finger prick test, right? So some of those machines use capillary action to pull the blood sample up into the testing strip. So if you poke your finger and you have the little bead of blood, you just have to touch the end of the strip to it, and it pulls the blood up into the strip. That's capillary action. Okay, so they're designed in a way where the blood will be kind of pulled up due to this phenomenon. So this is also another thing where it's partially responsible for transporting water from roots up into the leaves of plants. So that's kind of where you might have heard that before in biology. So here is a water strider. This is not actually a spider, it's a strider. He's striding on the water. Geckos also can do this. There's various like small little insects and small reptiles and things that can do this, tiny little frogs. But the pressure or the force of these creatures is less than the surface tension, so they can just walk on top of the surface. Okay, so this little water strider is not very heavy. Okay, he's little, so his mass is creating a small enough force that it's not going to break the force between the molecules on the surface. One of our last things to talk about here with liquids is that you do have vaporization and boiling. So again, obviously this is going to be unique to liquids because they're the only state of matter that's going to be like set up for this. So evaporation and boiling are two different things. So keep that in mind. So if you think about it this way, if you think about boiling first, right? Boiling is just changing your liquid into bubbles of vapor that are going to appear throughout the liquid. That's the boiling. The boiling is happening under the surface. It's like, if you're boiling a pot of water and you get those little bubbles along the bottom, that's the boiling. Okay, so when they come up to the surface and they're released, the gas, the water vapor is released, that's going to be your evaporation. Okay, so the evaporation is when the particles of gas actually escape from the liquid. Boiling is when those particles of gas are just formed within the liquid. So they're both formed in the same way. You're adding a lot of energy. The liquids become more spread out, and then they form these little gas pockets and escape. But just keep in mind that those are two different processes. The last thing of liquids, property for liquids, is that they can form solids. Gases could also form solids. It's much, much less common. So we know that when a liquid is cooled enough, those attractive forces they're gonna lose most of their energy, right? So if you have water and you cool it down and it's almost about to freeze, it has very little energy. Okay, so the particles are moving around very slowly, and because of that, the attraction between the particles is stronger than the kinetic energy. So they kind of form together into this more regular repeating pattern. And we're going to talk about those in a minute. So just be aware that all liquids will freeze, just some of them not at temperatures that you would come across in daily life, like ethanol. Ethanol is a type of alcohol, and it freezes at negative 114 degrees Celsius. Okay, so that's about negative 170 degrees Fahrenheit. You're never going to come across that in a regular situation, but it does eventually freeze whenever you get it down that low. In theory, everything would freeze if it came to absolute zero. Absolute zero just means that there's zero energy in that substance. It's never actually been achieved. It's 0 degrees Kelvin or negative 273 degrees Celsius. So it's never happened yet. They've come very, very, very close to it, but probably sometime in your lifetime that will happen. So moving on to solids. So solids is obviously going to be our last property or state of matter that we're going to talk about here. Solids have a couple of specific things to talk about. And a lot of that kind of comes back to the regular repeating pattern that they go into. So particles in a solid are going to hold pretty much fixed positions. Okay, so you're going to have different kinds of solids. We know that any liquid, any substance is going to turn into a solid when it loses enough energy, right? So the kinetic energy, which is the energy of motion within that substance, is going to become so low that the particles, the actual molecules of the substance, are going to, the attractive forces between them will overcome the kinetic energy. So they're going to bond together, and depending on what type of substance you have, they'll form either a regular repeating pattern, which is a crystalline solid, or they will form amorphous patterns. So amorphous just means that, like, without a shape, they don't really have a definite defined shape. So most things that, and we're going to look at crystalline structures today, but you do have like quartz here, very regular repeating pattern, diamond, most minerals, things like that. You're going to have kind of this nice little structure. They do come in like different specific shapes, but we'll talk about that. Glasses would be an amorphous solid. Plastic is also an amorphous solid. Okay, so if you've ever noticed in an older house with really old windows, like really old windows, you'll notice that towards the bottom, they are kind of thicker. So if you ever are in an older house, like I'm talking like early 1900s, maybe late 1800s built home, look at the glass. So at the top of the window pane, the glass will be thinner, and at the bottom, it will be thicker. And that's because glass is an amorphous solid, which means it holds properties of both liquid and solid. It's not truly a solid because it doesn't have that regular repeating pattern to keep it in a fixed shape. So over time, gravity pulls on these particles since they don't have a very regular structure that's not very strong. And you can kind of think about that, right? So if you were trying to step on both of these shapes, this one would probably be easily compressible because there's not any points of support really, where these do have that. So glass, eventually over time, gravity kind of pulls this down and changes its shape. For a crystalline structure, which is most solids, they do have a definite shape and volume. Okay, so solids in general are going to maintain their shape. They will maintain their volume. They're not really going to change at all. It can change a little bit with pressure and temperature, but for the most part, your solid particles are very close to one another already, and it would be difficult to compress them or change them anymore. So if you're thinking about like the desk that you're sitting at, the surface of your iPad, I mean, these things are solid, right? Go pick up a rock from outside, you can't just squeeze it down and change its shape. Not very easily. I mean, I know that does happen with like carbon. So if you had a chunk of carbon deep underneath the Earth's surface, and the pressure of the Earth and the gravity at that point can compress the carbon enough to turn it into a diamond. That's how most of these like pretty gemstones are made. So that can happen, but those are very extreme amounts of pressure and very high temperatures. So those kinds of things can happen. They can change the shape of a crystalline structure, but it's requires extreme conditions. Another thing about solids is that they do have a definite melting point. Okay, so just like liquids have a vaporization point and a freezing point, solids have a melting point, right? So a freezing point and a melting point will be the same number, right? So for water, the melting point of water in Celsius, or sorry, in Fahrenheit is going to be 32 degrees, right? So water will melt, ice will melt at 32 degrees. It also freezes at 32 degrees, right? So kind of depending on which direction you're coming at it from will give you the definition of whether you're going to say something is freezing or melting, but you're going to have that like definite point. So any type of solid will have a melting point. And again, it's kind of the same as the liquids. Some of these melting points are going to be really, really high, and they're going to be at temperatures you're not really going to come across very much, like granite rock. So granite rock is formed from magma. So deep underneath the surface of the earth, you have these extreme pressure temperature situations. As that cools, it turns into granite or lots of different kinds of rocks. So you couldn't just throw a piece of rock in a fire and expect it to melt because the temperature's not high enough. Last two things to talk about are the density and compressibility. Solids, obviously, we've kind of hit on this before. They're very, very dense. Those particles are already very close to one another, so you can't really squeeze them down much more. You can just barely squeeze them down if you had really extreme situations. So in comparison to a gas, gases are highly compressible, liquids are slightly compressible, and solids are basically not compressible at all unless you have extreme conditions. Last thing here is that they have a low rate of diffusion. So think about that. Solids actually can diffuse, which is kind of strange to think about, right? So if you do have two pieces of metal and you clamp them together for a very, very long time, you will get a couple of molecules that have diffused and moved position. But again, these particles are very attracted to one another. They're not going to want to move. So that would happen at a very low rate if it happens at all. The last thing to talk about here is crystals. So we have crystal structures. This is what the assignment kind of focuses on today. We're going to talk about the different shapes of crystalline structures and kind of what those represent and maybe kind of the types of molecules that make up different types of structures, basically. So we know that crystal particles are going to be arranged in a three-dimensional lattice. Okay, so this is your crystal lattice or your crystalline structure. So when we talk about crystals, we're really just talking about solids that form into a regular repeating pattern. Okay, so these are just some examples down here, like iron on the left-hand side, chromium, there's a couple other examples there. Those have a more simple pattern, but they are regular and repeating. So that is going to be a strong structure, right? You go into the center, you have another, it's kind of cubic face, but it has different shapes within on the sides and within the inside of that. So that would be different types of metals. You have aluminum, nickel, copper, all that. And then on the right-hand side, hexagonal is just yet another formation, okay? So you have magnesium, zinc. So as we go through these, you'll kind of get some examples of those. So we know that the arrangement of particles is represented by a coordinate system. So it's a coordinated, regular, repeating pattern, and the pattern is repeated of unit cells, okay? So if you think about a sample of salt, right? You could break that down all the way down until it's just one singular molecule of sodium chloride, okay? A unit cell is kind of the same idea. So a unit cell is going to be one singular formation of that solid, and then it would grow from that point on. So you can have lots of different types of symmetry with crystals. These are kind of your most common ones, and these are the ones we're going to talk about today with your assignment whenever you get to that. So this is what these shapes look like if you were to draw them out, right? So you can kind of see here that they have different angles with them, like the two on the right-hand side, monoclinic and triclinic. Those are very similar. The only difference really is that they have different angles at them. So that will be important to pay attention to in the assignment, because that's going to be something that you use as we move forward in class. So the pictures at the top are going to be larger examples of them. So if you want to think about the bottom portion of this picture as the unit cell, like this is what they look like on a microscopic level. And then the macroscopic level would be these crystals and kind of what they look like as they grow and form. So you might find something like this on Earth, if you were searching for it. You might find these substances, these rocks, and you could refine them, right? But if you broke them all the way down, they would have these little shapes, making them up. So there are 4 binding forces in crystals, and we're going to talk about that really quick, and that's the last thing. So ionic crystals are going to be very, very strong, okay? So crystals that form between ionic bonds, we already know that ionic bonds are very strong. Okay, we've talked about that last semester, because you have a positive and a negative, right? So you are transferring electrons from one to the other. They are bonded together very, very strongly. So these ionic crystals are very strong. They're very hard. They're going to be brittle. So if you do break them apart, they're just going to kind of fracture and come apart. It's going to be really hard to melt them, so they're going to have high melting points, and they make good insulators. Covalent molecular crystals, these are going to be covalently bonded molecules that are held together kind of loosely, okay? So these are very weak. So your covalent bonds, we know, is like a nonmetal with a nonmetal. So these are going to have really low melting points. They're very soft. They're easily vaporized. They're easy to break down, basically. So just remember, where ionic is very strong and covalent is a weaker bond. Okay, so here's some examples of that, right? So an ionic bond, you're going to get this very strong, regular, repeating crystal lattice. So here we have like an example of a salt. So lithium chloride, nice crystal lattice there. On the right-hand side, you have water. So this would be like if you form ice, right? So if we cool it down, we're forming ice. These are all still going to be covalent bonds. They're going to be easy to break down. So it would be easy to melt water. It's easy to break apart ice. The last thing to talk about is going to be metallic crystals and covalent network crystals. So metallic crystals are going to be crystal structures that are only made of metals. And we touched on this last semester when we were talking about ionic versus covalent and metallic, right? So with these, we know that the metal, the bonds, a metallic bond is an interesting type of bond, because all of the electrons become delocalized and they just kind of move around. So we called that a sea of electrons, if you remember. So we have the metal ions, and then their electrons have kind of floated off and they're just going all over the place. So again, these metallic crystals still have a regular repeating pattern because they have crystallized, but you can melt them. They're going to have a high electrical conductivity because of the electrons moving around so easily. And the very last thing to talk about is the covalent network crystals. Okay, so each atom is going to be covalently bonded to the neighboring atoms, right? So these create really, really large networks with large numbers of atoms. So these would be huge, huge molecules, right? These are going to be very, very hard. They're going to be very brittle. They're going to have really high melting points. So covalent network crystals are very strong. So if you're trying to compare all of these, you could say that ionic crystals and covalent network crystals are very strong, whereas metallic crystals are less strong, and the weakest of them all would be covalent molecular crystals. Okay, so that's all we're going to go over today. I know it's quite a bit, actually. So look at the assignment. Please let me know if you have any questions. You are responsible to do a little bit of research on your own of the crystal shapes. So these guys. And this you will want to keep somewhere because this is also going to serve as a resource for you as we move forward in this unit. So please let me know if you do have any questions over those things, and I will talk to you guys next time.